Right, hello gang, welcome back to our Physics 8B live stream. This week is going to be EM waves, and we're going to get this topic in right before midterm 2, which is next week, which should be the last topic on midterm 2 for that matter. And so we're going to go over EM waves, we're going to describe them. We'll see they're not that bad once you understand what you're dealing with and the few things that you are responsible for, because it turns out there aren't that many. EM waves are they're rather doable, I would say. So not a bad chapter, especially since we're coming off of magnetism and induction, which were much bigger and much denser chapters. But this is going to bridge the gap between magnetism and induction and electric field stuff we did before, and optics, which is what we're going to do next. Okay, where we're going to study, formation of images because of lenses or mirrors. And yes, we will deal with light. We won't necessarily really look at the electromagnetic nature of light, but it'll be a first step in the direction of studying light. So we'll do optics. It's very geometric. It's pretty straightforward. And then we'll do interference and diffraction, where we're going to come back to what we're going to introduce today and say, okay, well, light is an EM wave, and therefore, we can have interference, we can have diffraction, and we need to talk about what happens in those experiments and why they're relevant. So we're moving out of the part of the course that could be, summarized as the story of charge in a way, really to get to the story of light, which truly 8B is the story of light, macro, but, it doesn't really look like it for the first 2/3 of the course. Anyway, today we're going to talk about EM waves. We're going to, introduce a whole bunch of new stuff that if you haven't done mechanical waves in Physics 8A, then it's really going to be new. If you were lucky enough to have someone who does treat mechanical waves in 8A, then this is going to look very familiar. It's the same mathematics as mechanical waves. It's just a different type of wave as far as its fundamental properties and, of course, what it's made of, because mechanical waves consists in requiring a medium to propagate and having the particles of that medium oscillate. Here an EM wave is going to be an oscillating electric field and magnetic field simultaneously. So we'll get started with that in a minute. For those of you who are new, welcome. Thanks for joining. You can find everything that I do in these videos, including the videos, the problems that I solve, as well as the homework solutions, on Slackademia. So go check us out, slackademia.com. If you go to the study guides page, you can sign up for this Physics 8B live stream course. It is a free course. You don't need to enter your credit card, anything like that. And like that, everything is in one place. So let's perhaps start by just drawing an EM wave, because an EM wave, it turns out, is quite unique, and it's going to be a three-dimensional creature. So I'm going to call this maybe the y direction, maybe this is the z direction, and then I'll make the direction x here the direction of propagation. And what we've learned so far in induction and in magnetism and electric fields and everything from before is that, well, there are two things that we learned. And for the most part, this falls under the induction chapter. We've learned that if I have a magnetic flux that changes, I get an induced EMF. It turns out with it, I get an induced electric field as well. And so a varying magnetic field creates an electric field. And then Ampere-Maxwell says that a varying electric field creates a magnetic field. So in other words, an electric field, if it varies with time, will induce a magnetic field, but then if the magnetic field varies with time, it will induce an electric field, and so on and so forth. And EM waves have both. They have an electric field that is going to vary with time, that is going to induce B, but as B varies, it induces E, and back and forth and back and forth. And so you get something that looks like this. Okay, and I'll do my best here. But you get a wave, okay, that oscillates in the y direction Now this is going to be E max, or sometimes we call it E0, the amplitude of the electric field. But the electric field is going to oscillate in the y direction as the wave propagates down the x direction. But simultaneously, there's going to be a magnetic field that's going to oscillate in the z direction as the wave propagates down the x direction. It's going to look something like that. Okay. So this is going to be B max, sometimes called B0. Okay, but B is always along z, and E is always along y. So E and B are perpendicular to each other, and x is going to be the direction of propagation here. So we have this weird thing, which is a wave, so it's a disturbance, that consists of an electric field and a magnetic field perpendicular to each other that oscillate and propagate in a given direction. Now in theory, it could propagate in all directions of space, but we limit ourselves to propagation along one direction, call it x for example, and we also limit ourselves to what are called planar waves. In other words, the wave front, in other words, the picture of the wave at any moment, is formed of an electric field and a magnetic field that form a plane. This plane is at all times perpendicular to the direction of propagation. Right here, this plane would be like this. Here it would be like this. But the plane itself is always perpendicular to x. So the direction of propagation, if it's x, is simultaneously perpendicular to both E and B. All right. So, and it's not always obvious that we'd like to draw things like this. So let's imagine we look down the x-axis with the wave coming at us. What we would see is, well, first of all, the x-axis, that would be the direction of propagation, right? So let me put it here. This is x. And, well, there's two possibilities. Half the time, the electric field is going to point up, and half the time it's going to point down. And it varies, right? It goes from 0 to E max back to 0, and so it oscillates. And half the time it points up, half the time it points down. And when it points up, the magnetic field that's associated with it points to the left, and when it points down, the magnetic field points to the right. So the magnetic field also oscillates in the z direction, and half the time is to the left, half the time is to the right if I'm looking down my direction of propagation, my axis x. Right. So if you were to draw an EM wave, that is what it would look like, and you could also draw it like this. It's a little bit easier to have a 2D drawing than this 3D drawing here. Okay. Now the wavefront, which is the plane formed by E and B, is perpendicular to the direction of propagation. We said that before, so let's write that down because that's an important property. And therefore, not only are E and B perpendicular to each other, but they're also perpendicular to x at all times. Now, how fast might a wave like this propagate in the x direction? Well, that depends on the medium through which the wave propagates. But if we assume that the propagation occurs in air, then the speed of the wave in either a vacuum or in air is going to be the speed of light, which we denote by c, and which is equal to 1 over square root of mu naught epsilon naught. And that's 2.9979 and a whole bunch of other digits, so 2458, whatever, times 10 to the 8 meters per second. That's way too much to remember. We're going to call it 3 10 to the 8 meters per second, and we're going to be pretty happy with that. Okay. Now, a couple of observations. The first one is that it should be remarkable, hopefully, to you that the speed of light, which is made of an electric field and a magnetic field, is only a function of mu naught and epsilon naught, which are the constants that we had in Gauss's law and Ampere's law that are proper to electric fields and magnetic fields. Which, I mean, it should be mind-blowing. Like, it's incredible that it's that simple. That is all it depends on. And so that will be the speed of the wave, and as we said, assuming we travel in vacuum or in air. Now, we don't have to travel in vacuum or in air, and we'll see what happens in the next chapter if we enter a transparent medium, such as glass or plastic or water, media through which light is comfortable propagating. Right? Now, light does not need a medium to propagate. Right? It can go from very deep in space through a whole bunch of nothing and then land on the Earth, so it does not need a medium to propagate, but it can also propagate in some media as long as they're transparent. Right? It does not propagate very well in sauerkraut, for instance. However, in plastic or glass, sure. And it slows down, in fact, if it travels in plastic or glass, but more on that next week when we talk about optics, okay? Because we'll talk about Snell's law and the index of refraction and so forth. Okay. So one of the important things that we need to do when it comes to a wave is to be able to describe it mathematically. It's probably the most challenging part of the chapter. Now this is going to go back to stuff from 8A, from mechanical waves, if you learned it back then, and if not, well, it's just going to be brand new. Okay, so let's go over the mathematical description of EM waves. And I'm going to make a little copy of this thing here, maybe, just to have. So let me bring this down here. I'm going to clean some of this up. Okay, so I just want a little copy so that I can refer to it over here. Now we're going to have to describe the fact that the electric field and the magnetic field are waves. And so, yes, the electric field oscillates along y, but the whole wave itself propagates down x, so we have to capture that. Now, we are going to write E as a function of two variables. The first variable is going to be the direction of propagation, which is x. The second variable is going to be time. The amplitude is going to be E max. That's the largest that the electric field is going to be. And then we're going to write it like this. Cosine kx plus or minus omega t plus phi sub c, where the phi sub c refers to cosine. So that's the phase constant if I'm using cosine. And that's because I could choose, instead of cosine, to use sine. It doesn't matter. So the electric field, in the case of the waves that we are going to study, is going to look like this. And you are free to choose cosine or sine. It doesn't matter. Once you have chosen cosine or sine, you just keep that for the rest of the problem because it's going to impact what the magnetic field looks like. But we're going to start with the electric field. Okay, now, the electric field is a vector. That's what I wrote here. But here I didn't write a vector, I wrote a number, so that's a problem. I need to add direction to the right-hand side of my expression here. And I'm going to say, well, it's j hat, right? It's j hat because the electric field oscillates in the y direction. So that's going to give me my electric field both as a function of position and as a function of time. And so we need to define all these quantities, right? We need to say what Emax is, what K is, what omega is, and what phi sub C or phi sub S is. And once we have all of that, then, okay, we can move on to B. It's very easy to get B if you know E, and vice versa. But let's assume that we start with the electric field. So what you need to know is that that's what it looks like. And that's a given in a problem, or at least it's a given in the sense that you should know it, and you can write it down. And then you can find all the different terms. Usually that's the game. It's to find the amplitude, K, omega, phi, for a given wave, and then use that to find B. Now, a quick reminder, if you've learned about waves before, the distance here from peak to peak, which is really the length of the fundamental pattern that repeats throughout the wave, is going to be called the wavelength. This is lambda. Okay, so lambda is the wavelength. It represents the length of the fundamental pattern that repeats. You don't have to measure it from peak to peak. You could measure it from, here to here. It would be the same thing. You could measure it from here to here. It would be the same thing. The point is, lambda represents the length of the fundamental pattern. It is, in fact, the distance that the wave travels in one period. Of course, if you don't know what a period is, that doesn't help. So we will get to that in a second. Okay, so I say that because as we go through each term, we're going to need lambda, and then we're going to also need the period t. Okay, so Emax is equal to the amplitude of the electric field. And it's going to be in volt per meter because it's an electric field. And it is the greatest value that you will achieve either in the y direction or the minus y direction. But it's the strongest the electric field is going to be. That's the amplitude. Then K is called the wave number. So we have the wave number K, and K is 2 pi over the wavelength, lambda. And that's going to be in 1 over meters. And I'm going to say where lambda is the wavelength, just to be clear. Now, the wave number does not represent anything physical or tangible. It's a construct. Lambda represents something physical. It's the length of the fundamental pattern, but 2 pi over lambda doesn't do anything in terms of representing a physical quantity. What it does is that it allows cosine every time x hits 1 wavelength, 2 wavelengths, 3 wavelengths, and so forth to reset, because then you're going to hit 2 pi here. Right? So if I have kx is 2 pi x over lambda, every time x is lambda, 2 lambda, 3 lambda, I get 2 pi and my cosine resets, which makes sense. Every lambda, the pattern should reset. So it's a construct to make sure that happens with sine or cosine. That's where the wave number comes from. Then we have the angular frequency, which is omega. Now omega is 2 pi times f, the frequency, or better put, 2 pi over the period, t. That's going to be in radians per second. Okay, that is where f is the frequency and t the period. And we'll define those underneath in a second. Okay, but your angular frequency, it's the same idea as k. 2 pi over t doesn't mean anything. T is the period. Okay, t is the time it takes for the wave to repeat itself, for the same pattern to occur again. So it represents something physical, but 2 pi over t doesn't. But in the same way that we have 2 pi over lambda here for k, because k multiplies x, omega multiplies t. So omega t is going to be 2 pi little t over period, so that every time little t hits 1 period, 2 periods, 3 periods, I get 2 pi, and I reset my cosine or my sine because every period the same thing should happen again. So these are constructs to make cosine and sine reset every time you hit a wavelength or a period, which of course there's got to be a connection between the two anyway, but that's good enough for now. That's what that means. So seek no significance in k and omega in and of themselves, other than to say that they're related to quantities that do have a physical meaning when it comes to the wave, which are lambda, frequency, and period. Now, let's define formally lambda, f, and t real quick. Okay, so lambda is the length of the fundamental pattern of the wave. T is going to be the time, or let's say, well, let's do t first. T is the time it takes for the fundamental pattern to repeat. And then F is the number of oscillations per second. And by the way, T is 1 divided by F, which is equivalent to F is 1 over T, of course. Okay, but the 1 here stands for 1 second divided by the period, tells you how many oscillations you have in 1 second. Okay, so if we want to make this relatable, right, if you imagine that you're on the sea, far away enough from the shore that the waves aren't crashing, they're just coming in, right, but they're not crashing yet, then the distance between this wave and this wave, that is going to be lambda. The time it takes for the buoy here, as the wave propagates toward the shore here to the right, the buoy is going to bob down and then back up. The time it takes to go down and then back up, that is 1 full period. Okay, and how many times it does that in 1 second, which is probably not very many, would be your frequency. Okay. Now, because of what I just said, it ought to be clear that there's a relationship, which is that in the time it takes the buoy to bob down and back up, which is 1 period, the wave has to move forward 1 wavelength. And that's a fundamental property of waves, which is that a wave will travel 1 wavelength in 1 period. And that has implications on the speed of the wave, which we'll get to in a second. But that's the relationship between the two. So those are quantities. Again, hopefully you've seen them already. If not, well, it's never too late to learn them. And that is how they come into play when it comes to K and omega in this expression for the electric field that we have. And then finally, we have to address two last things based on these expressions. We have to talk about the plus or minus thing going on here, and then we have to talk about phi sub c. And we'll do problems where, we find all these things, and it'll make a lot more sense. But for now, we at least have to cover why the form of electric field is what it is and what these terms mean. Right. So now kx plus or minus omega t. All right. If I have kx plus omega t, the wave propagates along minus x, whereas if I have kx minus omega t, the wave propagates along plus x. Okay. Hand-waving explanation of that is if you plot all this versus this, in one case looks like the wave goes to the left, the other one it looks like it goes to the right. That would be a mathematical explanation. There's a better explanation than that when it comes to how x is related to t within this expression. But we're not going to worry about that. I mean, that's a little too far. The point is you can just memorize this, okay? Weirdly enough, if it's ks plus omega t, you go along minus x. If it's kx minus omega t, you go along plus x. Okay. All right. And then the last quantity is phi sub c or phi sub s, right? Now I call it phi sub c if I'm using cosine, phi sub s if I'm using sine. That's because they're never the same thing, right? So I would just want to put in your brain that phi for cosine is going to be a certain value, whereas if you had chosen sine, you would get a different value of phi. But phi is called the phase constant. So these are phase constants. That tell you what happens at x equals 0 when t equals 0. Or more generally speaking, at any given location at a certain time. If you tell me the location x is 2 meters and you tell me time is 3 seconds and I know what happens, I can also find the phase constants. But that's more complicated than just saying, okay, well, what happens at t equals 0, at x equals 0? That's usually the go-to. Okay, so it's a bit of an abstract notion of, like, okay, phi is what? It's a phase constant, okay, but I don't understand how it tells me what happens at t equals 0 and x equals 0. Now, exactly what happens, well, exactly how to find phi, the mechanics of it, we're going to go over in a problem. But as far as understanding what these phase constants represent, they represent the following. So let me just draw a wave real quick. Okay, so it's going to be something like this. By far not a perfect wave, but it's going to get the job done. All right, what you're doing with phi is you're taking cosine or sine, which, by the way, cosine and sine are identical curves, right? They're shifted, obviously. They're not on top of each other. If you graph them on a calculator, you see two curves. But if you were to slide a cosine over until it was on top of a cosine, you couldn't tell the two apart. They're the exact same shape. All right, and so what we're saying is that, okay, well, if this is E here, the electric field, and this is X, and this is X equals 0, it's the origin, and T equals 0, I have something. Well, what is that something? Is it the case that the electric field is equal to this at T equals 0? Doesn't have to be. It could be anything else. And so what phi does, for either one, for sine or cosine, is it slides this curve to the left or to the right. And it slides it to the left and to the right so that whatever happens at x equals 0 and t equals 0 matches what you have in your problem, right? So it takes this very general form of E max cosine kx plus o minus omega t plus phi sub c, or the same thing with sine, and it says, well, why don't you tell me what kind of wave you have? And then with phi, you'll be able to tweak this expression to slide the curve left to right so that your mathematical description matches the wave that you are dealing with. Okay, so that's what phi sub c or phi sub s does. And again, we'll see this in problems. So the conclusion of all of this is that the electric field is going to be given by one of these two expressions. Doesn't quite matter which one you choose, you just have to choose one. Okay. And once you've chosen one, you have to stick to it, right? You can't just go change around cosine and sine in the middle of a problem. You wouldn't want to do that. But this is going to be your electric field, and from there we can derive the magnetic field. Now, there we go. Let me just grab this again, just so that we remember that the magnetic field is propagating, or oscillating rather, along the direction z here. Once you have your electric field, your magnetic field is going to have the same form. So if you start with cosine for E, then b of x and t is going to be simply b max. But then it's going to be the exact same cosine. No different, right? So you've already found k, omega, phi, and everything. So it's going to be the same thing because E and B are in sync, right? When E is max, B is max. When E is 0, B is 0, right? When E is minus E max, B is minus E max, right? So it's going to be important to reflect that. Hold on. I screwed this up now, didn't I? By saying that, okay, if I find E with cosine, then it's going to be the exact same cosine in B. Or, of course, if instead I used sine, then B is going to be B max, the exact same sine, kx plus or minus omega t plus phi sub s. The only difference, there are two differences. The only difference in here is, okay, phi sub c is not phi sub s, right? So those are different, but whatever you found here, you're going to get the same one here. Whatever you found here, you're going to get the same one here. That's my point I'm trying to make. So if you have this, then you get this. Whereas if you have this, then you get this. The second difference is the direction along which B oscillates, which is going to be k hat instead of j hat because B is along the z-axis. Okay, so that's the mathematical description of waves, and we'll apply this to a problem to see how you find all these quantities. Now, allow me to just quickly make a copy here because I ran out of space. But I'm not quite done. We're going to go over the properties of EM waves so that we have everything covered before we do practice problems. Okay, so let's talk about properties of EM waves. All right, so first of all, EM waves can propagate through vacuum. They do not require a medium to propagate. So they can propagate through empty space from distant stars and shine onto the earth, and we can see the light. Okay, so they don't need a medium to propagate. They do not care. Okay, EM waves are also transverse waves. So EM waves are transverse waves. Now, a transverse wave is a wave for which the quantity that oscillates is going to oscillate in a direction perpendicular to the direction of motion. Okay, so E and B oscillate perpendicularly to the direction of propagation. That's the definition of a transverse wave, right? So if the direction of propagation is x, E is going to be along y perhaps, and then B is going to be along z. But they oscillate along those directions that are perpendicular to x. All right. Then EM waves propagate in the direction of E cross B. Oof, here we go again, a cross product. This is not our first cross product, is it? FB is QV cross B, or IL cross B. We've seen other cross products, but those are good enough. The point is a cross product is associated with the right-hand rule. So if I say that EM waves propagate in the direction of E cross B, well, I need to associate this with the right-hand rule. Okay, now this is going to be the thumb of my right hand. This is clearly going to be my forefinger, my middle finger, and try to draw the other fingers something like this. This is why I majored in STEM, by the way, because yikes. But the point is, my forefinger is going to be along E. My middle finger is going to be along the magnetic field B. these two will always be 90 degrees from each other. Okay, that's not always true for every cross product. Okay, I'm not saying that because it's E cross B, it's 90 degrees. I'm just saying because it's E and B in an EM wave, then it is 90 degrees between the two. And then your thumb will give you the direction of propagation. So that if we go back to what we had drawn initially, where we had the propagation out of the page, right? I had said E spends half of its time upward, like this, and half of its time downward, like this. Well, if I want this wave to propagate out of the page toward me, forefinger long E, my middle finger, in order for my thumb to point out of the page, has to point to the left. That will be the direction of B. Whereas here, if E points down, my middle finger has to point to the right so that my thumb points out of the page, and B is going to go in this direction. So I kind of cheated. I used it in reverse. I said I know propagation, let's find B. But of course, you could just find it to find the direction of propagation. If you're given E and you're given B, forefinger long E, middle finger long B, your thumb's going to come out of the page, and that'll tell you the direction of propagation. So you have to be able to go both ways, right? Either find propagation because you know E and B, or you're given propagation in one of the two and you find the third. But it's from the right-hand rule. Okay. And so last few properties, speed of an EM wave. Now we already touched on this, but it is going to be, in the case of propagation through vacuum or through air, the speed is going to be c, which is the speed of light, 3×10⁸ meters per second. However, if it's propagating through a transparent medium, and we'll review this next week, the speed v is going to be c divided by n, where n is the index of refraction. Now, it tends to be the case that we never worry about this kind of scenario until we reach optics, so we kind of only focus on EM waves traveling through air or vacuum in this chapter, and then when we get to optics, we're like, okay, well, let's talk about the index of refraction because I need it for Snell's law, and then how does that affect the speed of the wave if it propagates through a transparent medium. Okay. And then I don't know what to call this is my problem. I don't know what to call it because I just gave you speed of an EM wave. Right? But basically the property of a wave is that its speed is a function of the medium through which it propagates, or the lack of medium through which it propagates for that matter. But it's set, right? If air doesn't change in any way, speed of light is c. And the transparent medium, same thing. If I don't change anything about it, the speed is going to be v. And so, yeah, that's true. If you just want speed, it's either c or c over n. However, there's a relationship between speed, wavelength, period, frequency, omega, and k, and I don't know what to call it. And so I'm going to say instead, in general, for any wave, meaning irrespective of whether it propagates through vacuum, air, or a transparent medium, we have the following, and this deserves to be written in a different color. V, the speed of the wave, is going to be its lambda wavelength over its period t. Because in one period, a wave travels one wavelength at constant speed. So wavelength over period is going to be speed. 1 over t is frequency, and this can also be written omega, the angular frequency, divided by k. This is how these quantities are related for any given wave, irrespective of whether it propagates through a vacuum, through air, through water, doesn't matter. Okay. In fact, it doesn't even matter if it's an EM wave. This is true for mechanical waves as well. And then the last property is that at all times E is equal to C times B. Okay, so this goes back to what we were saying. They're in sync. When E is max, B is max. When E is 0, B is 0. When E is min, B is min. Okay, they're always related through E is equal to CB. Okay, so that's a lot to chew on right there. So rather than add anything more to this, because there's a little bit more I want to add, let's go do a problem. And then the stuff that I haven't added yet, which is intensity for EM waves, we can touch on when we do the polarizer problem after this one. Okay, so we have a plane EM wave that propagates in vacuum. So we know that it propagates at the speed of light. And at time t equals 0, we're given the electric field that's along the x direction, and the wave propagates in the plus y direction. Okay, so we're given this graph, and we're told, write the mathematical expressions describing the variation in space and time of the electric field and the magnetic field vectors using the numerical values extracted from the figure above, blah, 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 blah. Okay, in short, find E and B, just like we wrote before. Okay, so we know what form to look for them in. We then have to find the amplitude, K, omega, is it plus or minus omega t, in kx plus or minus omega t, and the phase constant. Okay, but this is super classic problem. I mean, guaranteed that if you have waves on the midterm, and it's just an EM waves problem, this is going to be on it. There's no way. Like that plus maybe a polarizer question in a two-part problem, but I'd be very surprised if there's none of this. So let's just go through it and get the information that we can get out of this graph and write the mathematical expressions. Okay, so this graph here, what does it tell me? Okay, it tells me the electric field versus y. Okay, and it's pretty clear from the graph that the electric field is going to oscillate over time between two values, right? 600 and in fact minus 600, not that it really matters, but what it tells me first of all is that E max, which is the amplitude of the electric field, is going to be 600 volt per meter. Okay, so I got that out of it. Then I can also get lambda. Lambda is the width of the fundamental pattern. So lambda is going to be this. I mean, you could argue that lambda is also this, that's true, but it's a little bit easier to find this here. So, you know, if this is 200 here, I would expect this to be 400, and I can say that the wavelength is going to be 400 nanometers. Okay. In addition, what else do we know? We know E oscillates along the x direction, and the wave propagates in the plus y direction at speed c, which is the speed of light because we're traveling in vacuum. Okay, so that's not bad. I mean, that's something, right? And given that, we are going to look for E in the following form. So we look for the electric field E in the form that we wrote above, which is E of two variables. The first variable is the variable for propagation. So we propagate along the y direction, so E of y, and t. Second variable is t. That's going to be E max, which I've already found. Cosine or sine, you get to pick. The problem didn't tell you, so you pick. I'm going to pick cosine. Cosine kx plus or minus omega t plus phi sub c x hat, because, or I hat, whatever. Call it I hat to be consistent, because x
is the direction along which E oscillates. Okay, well, can we find K?
Sure, we can find K. We know lambda. K is 2 pi over lambda. That's 2 pi divided by 400 nanometers that I have to put in meters, and so that's going to be 5 pi 10 to the 6, 1 over meters. I'd like to find omega.
Now the problem is I have no information whatsoever about period or frequency. Nobody gives it to me. But it's okay,
because based on what I just wrote above, I know that omega is going to be the speed of the wave times k,
right? And so omega is c times k.
That's going to be 3 10 to the 8 times 5 pi 10 to the 6, and that's going to be 1.5 pi times 10 to the 15 radians per second.
Okay, so that takes care of that. Then we're going to have plus or minus omega t, right? Well, that's going to be minus because we're propagating in the plus y direction. Okay. So we choose
kx. Now, I'm sorry. See, I made a mistake. I always tell students not to make the mistake, and then I made it. Ay. Should be ky. Okay. If it's y here, it's y here.
That's the direction, it's the axis along which you propagate, which is the y-axis. Okay, sorry. It's so common to write kx plus or minus omega t that I lost track of that. My bad. So careful, that's y.
We are going to choose ky minus omega t because the propagation is along plus y.
Okay.
And so then we have almost everything. We just have to find phi sub c.
Okay. Now phi sub c tells me what happens at t equals 0 and x equals 0. We said x equals 0. Really, it would be y equals 0 here. Okay, what happens in the direction of propagation at the origin when t is equal to 0? Okay, well, E is equal to E max at t equals 0, right? Because it's 600 volt per meter.
So we're going to say our initial condition is that at y equals 0 and t equals 0, we have E is equal to E max.
That's my initial condition. Could have been anything else, right? It would have been given by the graph. In this case, so it's pretty easy. It's easy to read and easy to write. At y equals 0 and t equals 0, E is maxed out. Okay, fine. So what does that mean?
It means that if I choose to write E, and I should add in the plus x direction. So if I write E like this, if I say E is E max, cosine of ky minus omega t plus phi sub c I hat, and then I say that at t equals 0 and y equals 0, it's equal to E max I hat. Well, this is, just to be clear, this is E in general, and this is just me saying from the graph I know that it's E max I hat. Okay, well, if y is equal to 0 and t is equal to 0,
these two guys go away. All right.
And so it has to then be the case that E max cosine of phi sub c is going to have to equal E max. It's the only way that can work, which means cosine of phi sub c is going to have to be 0, And there's only one angle for which the cosine, I said 0, it's 1, duh, which means phi sub c is 0. There's only one angle for which the cosine is 1, and that is phi sub c is equal to 0 radians.
Okay, so I found phi sub c. Said differently, if I want this expression to describe this wave that is equal to 600 volt per meter at y equals 0, at t equals 0, I need phi sub c to be 0. That's it. Okay. And so then the conclusion is the following. The conclusion is that E, as a function of y and t, is equal to E max, which is 600 volt per meter, cosine k is 5 pi times 10 to the 6 y minus omega 1.5 pi 10 to the 15 t plus phi sub c, which is 0, I hat. Okay? So I know E. So it should be very easy to find B. Right? The only thing I'm going to have to say is I need to find B max, and I need to find the direction along which I have B oscillating. So I know E. Let me then do the following. Let's do this. This is going to be X, Y, Z. Now I know that E at t equals 0 and y equals 0 is going to point in this direction. It's going to be E max for that matter. I know also that propagation occurs in the y direction. So by the right-hand rule, I need to find B so that propagation is in that direction. My forefinger has to be along E max, middle finger along B max, and my thumb will be along propagation. Now, hopefully you agree that then at t equals 0 and y equals 0, B max is going to be along minus Z. Okay. If it doesn't make sense, you can look at it from here. Okay, you can have y is the direction of propagation coming at you. Okay, the only way that my forefinger along E max and my middle finger along B max gives me my thumb out of the page is if B max points down. Okay, so B is along minus k hat at t equals 0 and y equals 0. And in addition, the only thing that I have missing, so I could write B of y and t, is B max. Okay, well, E is C times B, so E max is going to be, or B max rather, is going to be E max over C. That's going to be 600 divided by 3 times 10 to the 8. That's going to be 2 10 to negative 6 Tesla. And that's going to be B max. Okay. So really, if I want to put my conclusion down here, so I only have one conclusion, I have E of y of t is this, and then B of y of t is going to be B max, which is 2 10 to negative 6, the exact same cosine, because B and E are in sync. The only difference is that B is going to be along minus k hat initially, so I'm going to put minus k hat like that. And I found E and B for this wave. Super classic problem, completely fair game. Expect no less on a test if you have an EM waves question. Be very surprising to not get that at all. Okay, so with that said, let's move on to polarizers. And I have a problem here about polarizers, but we haven't said anything about them yet, so I'm going to go back and do a very brief recap. But I didn't want to overdo it. We had talked about so much stuff already that I figured it'd be nice to have an example to see how it all fits together. And then we can go talk about the intensity of EM waves, polarizers, and Malice's law. Okay, so intensity of EM waves. Now, intensity is an interesting quantity in physics. It's a quantity in general. It's not particular to EM waves. Intensity is power over area. But power is energy per second. So really, it's energy that flows through an area every second. It makes sense if you think of a solar panel, for instance. Right? How much energy strikes a solar panel every second? That's going to be the intensity of the EM wave. Okay. So intensity, typically denoted by capital I or capital S. I tend to use capital S because capital I is kind of overcommitted already. It's, current and circuits and all that. So S is going to be the power per area. In other words, it is going to be the energy flowing through an area every second. That's what intensity measures. Directly correlated to the brightness of the light. Okay, but it's a specific definition, so we have to be careful and give the proper definition. Now, you might say, well, I kind of get the idea, but isn't it the case that the electric field oscillates and the magnetic field oscillates? So doesn't that mean the intensity is changing all the time? It's like, yeah, actually, you are right. And so we don't necessarily talk about instantaneous intensity, although we could. We tend to look at the average intensity. Okay, it averages out to something, whatever that is. And, if you look at sunlight, you don't see it. You don't see the brightness, get dimmer and brighter as it oscillates. It goes too fast anyway. So when it comes to intensity, we tend to define the average intensity of an EM wave. And it's going to be given by 1/2 C epsilon naught Emax squared, if you want to express it in terms of the electric field, or 1 over 2 mu naught C Bmax squared, if you want to express it in terms of the magnetic field. Depends what you know. Doesn't really matter anyway, because E is C times B, so you could get from one to the other. If you know E, you know B, and vice versa. But if you want to find the average intensity of an EM wave, that would be it. Okay. So, let's briefly recap polarizers and intensity, or the effect that they have on intensity. Now, polarizers are interesting objects. They have a preferred direction, is what it's called, and they would prefer light to come in through that direction. Or at the very least, they make sure that whatever light comes in, the light that comes out is only in that preferred direction. That's a better way to think of it. So they'll take in any light you want, but they'll make sure that when the light comes out, it's polarized in a given direction. Now, the direction of polarization is very important, is the direction of oscillation of the electric field, not the magnetic field. We don't care. We care about the direction of oscillation of the electric field when it comes to polarization. So I'm just going to draw two simple scenarios because this is something that once you do a few problems, it makes sense anyway. So this is a polarizer, and what I'm showing here is the preferred direction of this polarizer. Okay. This polarizer has a preferred direction that's going to be an angle theta from the vertical.
Could be from the horizontal, it doesn't matter.
It's just some direction, let's say theta from the vertical. And it will accept any light coming in, but what it will do is it will make sure that the light that comes out only comes out polarized along this direction. Okay, so it'll let the electric field come out, but the electric field will then be such that it oscillates along the along the direction of the polarizer, the preferred direction of the polarizer. And there's going to be, of course, it suggests that whatever the intensity is after the polarizer, it's going to be less than before, because maybe a lot of light comes in, but you only let light out that oscillates along the polarizer. So how much intensity did you have before? Well, let's call it S0, and then let's call S1 the intensity after the polarizer.
Now there's two possibilities. Possibility number one is that, there we go,
you shine onto the polarizer unpolarized light from your flashlight, from the sun, from most sources of light have what's called unpolarized light, or produce unpolarized light.
That means that the electric field does not have a preferred direction along which it oscillates. Right? It's going to be all over the place. Right? It's going to oscillate in all directions of space. So we tend to represent it like this. So this is unpolarized light. And most sources of light that you'll encounter
in everyday life are unpolarized. Now, if that light comes in to the polarizer, and when it exits, it will be polarized because, duh, it went through a polarizer. So, okay, polarizers polarize light. Well, the brightness will have gone down, and the intensity S1 is going to be half of the original intensity. You lose half of the intensity if you go through a polarizer and you have unpolarized light initially. So that's one way, in fact, to create polarized light. You pay a price, you lose intensity, but you do get polarized light coming out of the polarizer. So that's one particular case. What you could then do is you could take polarized light here and shine it onto your polarizer. Okay, let's say you have polarized light that's polarized vertically initially, from a laser maybe, or maybe before that you put a polarizer and you were shining your flashlight through the first polarizer, it came out like this, and now there's another polarizer. Doesn't matter. The point is, the difference with the previous scenario is that the incident light here is now polarized. If it is polarized, when it hits the polarizer, like this, it's going to be a certain angle theta relative to the preferred direction of the polarizer. Well, the polarizer will only let light through that oscillates along its preferred direction. Okay, this is why we say polarizers are going to rotate polarized light. You've learned this probably in chemistry with enantiomers and rotating polarized light and stuff like that. But polarizer is going to take polarized light, and it looks like it rotated it. It was polarized like this. Now it's polarized like this. Okay, here it doesn't look like it rotated. The thing couldn't make up its mind. Okay, and then it came out like that. Okay, but here it started out like this, and now it comes out slanted like this. So it seems like it rotated the polarized light. And S1 is going to be given by S0 cosine squared of theta. Okay. Now this has a name. This is Malice's law. The other one doesn't have a name. The other one is what your GSIs call common sense when you ask them where it comes from. Then you want to kill them, metaphorically. But they'll be like, oh, it's obvious. Like, oh, no. But anyway, it doesn't have a name. Malice's law refers to the case where you have polarized light going through a polarizer and it emerges rotated an angle theta. Now, if theta is 0, right, the polarizer is like this, Well, cosine 0 is 1, so you don't lose any intensity because your light's already in the direction of the polarizer, goes straight through, nothing happens. If theta is equal to 90, your polarizer is perpendicular to the incoming light. Cosine 90 is 0, going to block all the light. So if you're polarized vertically, you hit a horizontal polarizer, no light comes through. Okay? So we could talk more about polarizers, but the truth of the matter is it boils down to this. And so let's see how you might apply that in a problem. All right. So here we have two polarizers in series. We have a plane wave, wavelength lambda. It is linearly polarized along the y direction, which is shown. Okay, cool. And propagates in the z direction in a vacuum. It's going to go through P1, which is 30 degrees from the vertical, and then P2, which is 90 degrees from the vertical. Okay? And we want to clearly indicate on the drawing the angles between the electric field, magnetic field, and the wave vector of the initial wave and explain. And then, which is going to look like stuff we've already done, but that's easy. And then calculate what fraction of the initial incident wave intensity gets through the second polarizer P2. In other words, the ratio S2 over S0. Okay, so let's start with the first question. The first question says, okay, I'm going to look down my z-axis. Polarized light vertically means the electric field oscillates up and down vertically. But what they want you to show is E and B given a propagation, let's say out of the page, given how you're looking at this. Okay, so we've actually already drawn this a couple of times. We're going to say, okay, well, E is vertical, right, because the wave is polarized vertically. So half the time it's up, half the time it's down. And then by the right-hand rule, what is B so that propagation is out of the page? Well, here it's going to have to be B to the left, and here it's going to have to be B to the right. Okay. That's it. That's all they want. Okay. So then, let's take this thing. Let me do this. I'm going to put that here. I'll just bring these guys down. And now let's find S2, the intensity of the light that emerges from the second polarizer. Okay. And let's just be methodical, go through each polarizer one at a time. We'll call this S0, that's the original intensity. Okay, so I start with polarized light. So I'm in the case where polarized light hits the polarizer, it will emerge polarized in the direction of the polarizer and rotate at an angle theta 1, because the angle that I want is the angle between the incoming light and the polarizer, which is this angle here, theta 1. So then light emerges from this polarizer along the direction of P1. Okay. It's going to have an intensity S1 when it emerges. Let me just, for clarity, draw the vertical here. Okay. And then this light continues on and reaches P2. Okay, but the thing is, when it reaches P2, it does not rotate through an angle theta 2. That's not true. It rotates through this angle here, which is going to be theta 2 minus theta 1. So that's 90 minus 30 is 60 degrees. Because P1 already rotated it 30 degrees. Okay? So now when it hits P2, it's, well, 60 degrees from P2 because P2 is horizontal. All right. So then, I'm going to apply Malice's law twice. Right? I don't ever go from unpolarized light to polarized light. I just go from polarized to polarized. So I'm going to write Malice's law. And I'm going to write that if we call the intensity of the light that emerges from P2, so this guy here, this is the light coming out of P2,
has an intensity S2. Then we're going to say that S2 is equal to S1 cosine squared of theta 2 minus theta 1. And then if we work our way back to relate S1 to S0, we're going to say S1 is going to be S0 cosine squared of theta 1. Okay, so the conclusion is that S2 is equal to, if I sub S1 into here, it's going to be S0 cosine squared theta 1 cosine squared theta 2 minus theta 1. And so that's going to be S0 times cosine squared of 30 cosine squared of 60. And cosine of 30 is root 3 over 2. If I square it, that's 3 over 4. And then cosine of 60 is 1/2, so that's going to be 1 over 4. So it's going to be 3 over 4 times 1 over 4 is 3 over 16. As 0, that's almost the right answer. They just wanted me to express the ratio S2 over S0, and that's going to be 3 over 16. All right, so polarizers, not that bad at all. There are a few things you have to keep in mind. The first one is that the direction that we care about, which is this direction here of polarized light, is the direction along which the electric field oscillates. Okay, so it doesn't matter what the magnetic field does, we can figure that out, but when we say direction of polarization, we mean direction along which the electric field oscillates. And then the other thing to keep in mind is that you have two possibilities. You either have unpolarized light hitting a polarizer, and then S1 is going to be S0 over 2 as it emerges, or polarized light hits a polarizer, and then it's Malice's law. But overall, polarizers are pretty nice and they're easy to deal with. All right, so that should wrap up EM waves pretty nicely. And next week it's going to be optics. It's going to look very different. In fact, it's going to look a lot simpler, much more straightforward and plug and chug, to a degree much more prone to memorization that actually works. Usually memorization doesn't work great in physics to solve problems, but optics is so systematic and so, just predictable and systematic that it's pretty easy to solve if you really know your formulas and your definitions. So it'll be a nice little break to cool off from midterm plus all this magnetism and induction. And then after that, interference and diffraction, 50-50, like some stuff's a little hard, some stuff's pretty straightforward. And quantum is quantum. It's as bad as they want to make it, so we'll do our best. But it actually doesn't necessarily get that bad unless you have a very heavily focused on math professor, let's put it that way. And some of them exist, Speleo, for example, but we'll deal with it when that time comes. Anyway, that's it for EM waves. Best of luck reviewing for midterm 2. I hope it goes well. If you need more help with Physics 8B, shameless plug, go to our study guides, slackademia.com. You can sign up for the study guide. There's all the lecture notes, all the solved problems, and all the old exams solved. It's $40 a month. You can't beat it. So feel free to check it out if you're interested. And again, best of luck studying. I hope it goes the way you want. All right, take care. See you next week.